Welcome everybody to the Space at VT seminar here for this September the 22nd, the first day of fall. Hopefully, I think it's actually technically in about an hour and a little bit more is the actual equinox for those, and it's not unreasonable that there's somebody in this crowd that probably knows that orbit parameter a little bit better than maybe the general public. But anyways, thanks for joining us. And today we have a good presentation here with Virginia Tech's latest CubeSat project. And we're speaking with Derek on UtProSat-1. So without further ado, Eric, take it away.
Yeah, thanks. So I'm Derek Whited. I'm the project manager for the UtProSat-1 satellite. And we are the next 3U satellite from VT to go up, and that launch will be next year in August. So we're working on about a year-long timeline to design, build, and test the satellite before flight. So the team structure has been pretty important for us. Trying to set up a sustainable team structure and something that can be built on and have people move up the ladder, so to speak, as this project carries on. So Dr. Black is the lab director for us here at the Hume Center and at Space at VT. Dr. Harding is the PI, so he's the person I report directly to. I'm the project manager, so I'm the student overseeing the rest of the students working on the project, and then we have our satellite subsystems broken down into lead positions. So Gustavo is leading the avionics or the core flight board and flight software team. That includes the UHF radio, the flight board, the power generation, distribution, and then GPS. Minzen Du is leading the integration team. So that's going to be chassis design and then managing requirements. Rob Engebretson is handling the primary payload, which I'll talk about here in a little bit. Zach Lefke is currently providing some subject matter expert area or subject matter expert information on the secondary payload, which is an S-band radio. And then Richard Gibbons is working on the tertiary payload, which is exposing memory chips to the space environment. And then finally, Shada Davaria is working on testing, so she'll be our interfacing person to go to for any test stuff that needs to happen. So the program goals are a little bit less technical and a little bit higher level than a mission goal that we might have. So the overall aim here is to develop a satellite design team that can be sustainable over multiple missions, instead of building a one-off satellite and having a one-off team that just exists for the amount of time that the satellite needs to be designed, built, and operated. The goal would be to have this turn into a team that can bring undergrads and graduate students on, give them the skills they need to work on small satellites, and then have them maintain VT's presence in space. So the first goal is establishing a reliable and repeatable methodology for the satellite design process. So that's going to be a lot of process control and just getting the team structure and decision-making structure set up and put in place that we can sustain the design process throughout multiple satellites. The second goal, maintaining documentation library, plays into that as well. There's been a lot of different methods for documentation on past satellite projects here at VT. So standardizing that a little bit, maintaining a documentation library, and then just adding to the level of documentation that we already have will help a lot. And then the last two are related to bringing students on and keeping them on. So driving student engagement for technical and project management. So empowering them to get involved in both aspects of the team, as well as giving them the ability to grow their skill set throughout their time on the team. And then finally, developing this team as a student talent pipeline for not only the graduate portion, but also for any companies that are interested in partnering with us and having access to students who already have a fundamental understanding of small sat design. So the experience that we bring to the table here goes back to at least 2018 with the VCC launch. Post VCC, there were a few failures that were noted, and that kicked off a need, or an identified need here at VT, to develop a standardized core or a standardized bus for a satellite that would be interchangeable across multiple missions and just provide a more reliable way to build a satellite sans payload. So following VCC, the next generation core project started, and that was mostly an on-paper design and a systems engineering level approach to designing software and hardware for that standardized bus. In mid-2019, we picked up thicksat, and thicksat was a small a sub-U CubeSat launch with an interesting payload to deploy a boom in space and take a picture of it. So there was some avionics and control board work done with thicksat, and NGC development continued alongside with a similar number and a lot of cross-pollinating between team members on both. So following thicksat, which was ended up being another failed launch where the satellite failed to be contacted post deployment, the NGC concept was revisited and became more important in the eyes of everybody here at VT. So this is where we get into UtProSat-1, which is combining the payload and the scientific goals of the thicksat launch that we were never able to accomplish, as well as the next generation core concept of having a standardized, rigorously tested bus. So those two combined are now in the UtProSat-1 team. So for a quick mission overview, the satellite is a 3U CubeSat. So that's comprised of 4 separate main sections. First section is going to be the avionics and the chassis. So that's going to be the NGC, or the next generation core style avionics package that I mentioned earlier. So that's going to be the flight board, electrical power system, solar panels, batteries, and the UHF radio. And included in that is the chassis if development for a chassis is needed. And that should be able to function purely by itself. So if any payload fails or the payloads just don't work, the goal is to still be able to contact the satellite and be able to do something so we know it's still in operating condition. The other 3 subsections of the satellite are all payloads. So the primary payload is a boom deployer, and this is a follow-on to the thicksat launch. So it unspools a flexible carbon fiber structure, and it has sensors to measure different aspects of that structure. The secondary payload is an S-band radio, and this is flying on board to help validate the VT ground station S-band capabilities, as well as match with a sister institution, ODU, that we're flying with to fulfill their goals. The tertiary payload and other passive payloads and passive experiments are flying because we do have extra room on board. The tertiary payload in question is a control board with memory samples on it, that will have a program running to identify bit flipping and return the quantity of bit flips back to the Earth. So the mission goals are a little bit more technically oriented and focused on just this mission rather than the program as a whole. And most of them will echo the program goals. So number one is leveraging all of our previous experiments to fly a successful mission. I think we've seen enough failures and lessons learned from previous missions that we can definitely apply all of those lessons to this one and have a better outcome as a result. Number two is demonstrating the effectiveness of the core itself. So basically getting flight heritage on the avionics package and making sure that the core functions of the satellite are able to work regardless of any other scenario. Number three is meeting all the objectives from the thicksat flight. So that's going to be deploying a boom and returning a picture of it. That was unable to be accomplished on the thicksat flight due to a power failure. So this is mission priority number one when it comes to things not related to the core. And then finally, using the 3U platform and the available free volume to perform other experiments and return that data as well. So visually, this is the priority level and the minimum success criteria for the mission, where we have the avionics and chassis requirements and criteria taking first precedence, and then the primary payload second, secondary third, and then the tertiary payloads are last in line for priority. So the minimum success criteria for the entire mission is meeting the thicksat mission requirements. So that would be deploying the boom and taking a picture of it. And then everything else goes beyond our minimum success criteria, after which we declare mission success. So the boom deployer is clearly the major payload flying on this flight. And there's a lot of external applications that are coming up that this can help a lot. So we have partnered with NASA Langley to acquire the boom material and get some design and technical information from them, so we can better perform our experiments. But following our flight, the NASA version of the mission will be flying on Artemis 1, and that's going to be called the HCS-3 mission. So it's a 12U satellite that's deploying 4 booms that unfurl a solar sail. So this is a small demo mission. The solar sail is not quite fully functional for actual propulsion, but the technical demo will be to maneuver the ACS-3 satellite in space using the solar sail and make small adjustments to its orbit. So this is the mission that we will be feeding our technical information to once we have it back on the ground. So laying out the payloads and payload requirements, a big part of our design process for the satellite has been establishing a hierarchy for requirements, as well as a hierarchy for mission goals. And you saw the hierarchy for the mission goals earlier, but the requirements hierarchy is totally related internally to the ground station. So everything, all the requirements that the ground station applies to the satellite are taken from the ground station avionics or the core package, and then from the avionics package, it's moved into the payloads. So this is a much more sequential way of organizing the requirements, where instead of letting science requirements dictate exactly how the satellite will operate, we're going to be working with hardware we already have So focusing on the hardware we already have and the hardware we can acquire, and then moving the requirements and setting limitations on the payloads is our focus. So from an operations standpoint, the core occupies the middle ground of the operation structure. So it's the choke point through, it's the choke point where communications from the ground pass through it, and then it affects some sort of condition on the payloads by turning on and turning off the power, and then the payloads pass data back to the core, which passes it down to the ground. The payloads and the core are only separated by power. So all of the payloads have their own control modules built into them. So any failure inside the payloads will not affect the operation of the core itself. So the goal here is to always have the satellite be able to be contacted and controlled from the ground, no matter what the payloads are doing. So early on, we established some off-the-shelf components that we're going to be buying, and then everything else is going to be custom designed and custom built. So a lot of the off-the-shelf components belong in the avionics and core section. So the onboard computer, the EPS, all of the radios, and then the power generation components. Those are all being organized into avionics and will occupy most of our off-the-shelf purchases. In addition to that, we have the UHF and S-band antennas, which you can see on the right-hand side of the render, as well as a customized 3U chassis to accommodate for the deployer that we're going to be launching from. So for payload 1, the objectives are a little bit more specific. This time around, we're testing a deployer that can deploy the boom and then reel it back in and deploy again. So a multi-deployment mechanism. We're also evaluating the reliability of the deployer mechanism as a whole, as well as the operating environment that it's going to be operating in. And then finally, NASA Langley would like us to measure the dynamic response of the boom when it's fully extended. So for the deployer itself, on the left-hand side is the thicksat single extension deployer. So that's something that's a mechanism that deploys the boom once, and it cannot be rolled back in. It deploys under the strain energy of the boom itself. So as you saw on the previous slide, it just spits out of the deployer. The UtProSat deployer is much more controlled. So the unwinding of the boom is done via 2 different motors. One motor controls the spool that the boom is wrapped around. The other motor controls several wheels that maintain tension on the boom. So this should be a much more controlled release and something that enables the mechanism to reel the boom back in for a different extension. Payload 2 is an S-band radio. So that's going to be more heavily integrated with the avionics section, where the S-band radio and the UHF radio will occupy the same board and some of the same power sources. So because we want to maximize our payload room for other objects, we're using the GomSpace AX100 and AX2150 radios. So these radios can be integrated onto one PC104 board, and it really minimizes the occupied volume of these radios. And then payload 3 is the memory exposure module. So that's going to be a stick of Intel Optane memory. And the goal behind this is to validate and get more flight heritage for this memory stick for future use in space missions. It's it's pretty space efficient as far as memory goes. So evaluating it now and making sure that it has minimal bit flips will help us integrate it into future onboard computers and other flight modules that we might want to fly. So as far as project schedule goes, we just had our preliminary design review a little bit earlier in September. So we've moved now from concept and preliminary design into detailed design and analysis. This detailed design phase will extend from now until January 2022. And that's when our critical design review occurs. Following the critical design review, which will roughly be around the start of the spring semester, the rest of the spring semester will be occupied with testing and evaluation, leading up to a pre-flight review sometime in May or June 2022. Following that, we'll just have final assembly and integration here at VT, and then again at Wallops following flight qualifications. And that integration will be with the launch vehicle. And then sometime in August 2022, we'll have our launch. And we are launching on NG-18, which is a Northrop Grumman CRS flight out of Wallops Island. So that's a quick overview of the mission. I have some more technical slides and a little bit deeper dives on power budget and data budget, but overall, that's the state of the mission up to now and what we're considering moving forward. So if you have any questions, I'll take them. Otherwise, you can email any of the 3 emails at the bottom of the screen. And for any further questions or any questions about volunteering or helping out.
Very good, Derek. Yeah, very good. Yeah, thanks a bunch for that. That's a good overview or whatnot. How far, I guess maybe I'll lead off a question or whatnot. How far, I guess you had your schedule of kind of where you're at, but I guess as compared to maybe other kind of with like UtProSat or something, if you were involved with that, how do you feel kind of in the timeline, like how far along you are?
Yeah, so at this point, I think we're getting a little stressed on time. And this is mostly due to getting information from third parties and suppliers. So the chip shortage has not helped anything, and it seems like all of the small sat suppliers are busier than ever with timelines for responding for requests for information and lead times and things like that. So I think moving forward into this fall, the biggest challenges are going to be acquiring parts in enough time to be able to test them and integrate them, and also just having a group of people on the team that are already knowledgeable about the subjects. So being able to work on software without a lot of supervision and being able to do mechanical design without a lot of hand-holding, that's going to be pretty key to keeping on schedule.
Yeah, it sounds good. I can certainly understand of that being a little bit of a stressful thing. There's a question in the chat of as a new grad student, how can they be a part of the UtProSat-1 team?
Yeah, so you can email me. My email is the first one on the list. And just to make things faster, if you want to send me your resume alongside it, so I can see, starting off what team you'd be a good fit for, we can get the ball rolling on that. We will need more people moving forward, especially when we get into testing, just because some tests might occupy times that not everybody can make it, and Some of the tests may be done on campus or off campus or at a third-party site. So having extra people who are already knowledgeable about certain things would help us out a lot.
Hey, Derek, I have a quick question. This is a
Yeah.
very cool mission and great presentation. I really appreciate you doing it. And I apologize if I missed this, but could you say what the data rate is on your comm system? How much data can you bring down?
Yeah, so here, there we go. So from a data perspective, we're still waiting on some information to get a really good picture of what our timeline will be. But our mission lifetime is going to be really short. So data is going to be a critical aspect. We're looking at about 5.2 megabytes total UHF volume. Because the S-band radio is an experimental payload, we're not going to be relying on that to get large photos or a lot of data down. But over the mission lifetime, we're looking at 5.2 megabytes total for UHF. That's about 2.5 to 3 weeks of total mission lifetime.
Why do you think, what's driving that short mission lifetime? Is it the altitude you're going to be deployed at?
Yep. So it's at the deployment altitude. I think we will be deployed around 250 kilometers, but I can't quite remember off the top of my head. That's the information we're currently waiting on, actually. Northrop Grumman has a low deployment altitude for all of their rideshare missions. And so far, they have been not giving us the deployment information that we're looking to get. So they're still in mission planning right now, which may end up with us just getting rough numbers until they can actually give us like the deployment orientation and the deployment velocity and things like that. But 2 to 3 weeks is a high estimate for a deployment altitude that low.
Sure. But there are still, I mean, that's a rare altitude to be able to get to. I'm sure if you talk to other people in the center, there's in situ devices they would love to put at 250 kilometers for such a short time. I could imagine a few things. So if you all plan a series of these in the future, we should talk more broadly within the center. And if you get that S-band, I mean, if Zach's doing it, it's going to work, right? That S-band transmitter and up the data rate. This all could be really cool.
And I fully agree with you on the on producing a series of these. That's going to be up to how many flights we can get a hold of and whether Northrop Grumman is going to continue flying the Antares launch vehicle. But the goal, everything that we're working towards on the engineering side is to have a ready-made satellite with as much free volume as we can get out of it for any payload. So that's kind of a plug and play situation. And if I may go back to here. So that green free volume is nearly 2.5 U in terms of volume currently. That may change as design changes this fall semester, but we can get the avionics package shrunk down quite a bit and crammed into one side of the satellite. So there's a lot of potential here for getting a lot of available volume for any payload that needs flight time in the future.
You think you could eventually fit not just an instrument, but some reaction wheels in there and get some fine pointing?
I think so. I think at this point that's more up to the power and onboard computer requirements than anything else. I know we can get magnetorquers to fit, but as far as reaction wheels go, if the person wanting the payload to be flown can take a hit on volume, that's definitely a possibility.
Okay. All right. Thank you. This is very cool, and I appreciate all of what all of you are doing.
Thanks.
Any other questions? Those here.
Regarding the technical documentation that he was talking about from the failures of the previous missions that we want to document, is it online and can I look onto it?
Yeah, so all of the previous documents for previous missions are on specific Google Drives. So you'd have to get permission from whoever manages the Google Drive to view it.
Okay.
If you're interested about joining the team, I can at least give you access to our Google Drive to start off with. But as far as prior documentation goes, it's a good primer on how to design a satellite, but a lot of the issue is that there's no standard format for how to document it. So what we're trying to do here is have a set document format that's more report style that should be able to get a lot of the information across. And there are examples of other schools and other CubeSat teams doing this, where for each flight they just update the technical document with more and more information, and that's the sustainable and like long-term way that I'd like to see us do it.
Yeah, we can have a wiki like that where we can document, because I come from India and there at IIT Bombay it has a very extensive Wikipedia wiki, not Wikipedia, but wiki pages where they document their entire satellite missions. And that is a very good resource to refer to. I had done that previously.
Yeah,
so
yep. Wikis are always nice. There are a few CubeSat teams that manage pretty extensive GitLab pages with a lot of documentation in there. So that's moving forward, that's something that we'll need to flesh out as we're working on this project.
Yeah. Okay. Thank you.
Yep.
I think following on to Dr. Bailey's kind of question, if you want to run through the your power budget or whatnot real quick, I think that'd be I too at least be interested to see, kind of what, because if you say you have 2.5 U for something else, you're generating a ton and that kind of thing.
Yeah. So I think the crucial part to talk about here is, rather than power consumption, even though we are limited on power and our EPS can only provide so much in terms of watts. I think you can have a pretty high wattage in terms of power consumption, but when we get into power generation, that becomes a more difficult conversation, because instead of just having the EPS and some batteries, then you need to talk about cost for solar panels as well. And deployable solar panels are double the cost of fixed, and regular flight rated solar panels are very expensive for a 2-week or a 1-week mission. So our power generation analysis is pretty rough right now, mostly because we don't know where we'll be deployed and what orientation will be deployed in. But in general, we're looking at barely breaking even on operating the avionics alone. So a lot of, in a perfect world, we'd be generating just enough power to make up for the operation of the avionics plus a little bit more to make up the deficit. But instead of just running the payloads all the time, our current strategy is to flip them on only when they need to be on and shut them off immediately after. So by power cycling all of our payloads, we can keep our power consumption fairly low over the lifetime of the mission. So this, we can probably follow up with just a power related seminar in the spring. But as far as it goes right now, if you have a power hungry payload, you're going to need to bring along some extra batteries to make that happen over just covering the satellite and solar panels.
Yeah, I got you on that, and I'm sure I won't dive into it too much here, or at least try not to. But there's certainly all sorts of questions and procedures and that kind of thing. If that's the case, where some previous flights, just to try to quickly highlight it, some previous flights have had problems with batteries that were charged up at some point, and then how long did they sit? How long did they discharge and that kind of thing? So
yep, power is a huge concern for us right now, and that's with the thicksat. That was what went wrong. The third-party provider for some of the equipment did not properly identify what the leakage current was of their flight board. So when they left it in the deployer for 2 months or 3 months, it just drained all of the batteries. So that's making sure we're constantly charged up. We're taking care of our EPS and our EPS batteries. We're cycling them right now. All of the maintenance behind power generation and power consumption is something that the team is very, very concerned about, because we'd hate to put something up there and then the only thing stopping it from working is the battery not being charged.
yeah, for sure. So, any other questions? Maybe, sorry, not to dominate too much or not to grill you too much. Just kind of continuing on that thought, and it can be kind of a quick answer is power generation or supply chain or something else you think your biggest concern at this point?
From a technical perspective?
Yeah, or just the whole, kind of getting to then.
Yeah, so I think on the project management side, people are going to be the biggest concern. And that's not to say that I don't have a lot of trust in everybody on the team, but the timeline is extremely short for building, designing, and testing a 3U satellite. So I think the crunch time work that the team does is going to be make or break for this mission working out and happening in the first place. On the technical side, I think power is definitely going to be the sticking point, and to go along with that, the volume constraints will be a part of it. So one issue with the deployer that we're using, which is the Planetary Systems Containerized Satellite Dispenser, is that the access ports are small on each side of the deployer and in a very specific spot. So for accessing charging ports, remove before flight pins, and things like that, you need specific locations open. And if we're talking about covering the exterior with solar panels, that can make things very difficult. So being able to place enough solar panels in the right area to still have access ports and to have some degree of uniformity to the chassis design and everything else, you can start swapping parts or reusing the design down the line. Integrating all of that together from a mechanical standpoint is going to be the biggest challenge with balancing power requirements, space requirements, and to a certain extent, machining cost for the chassis.
Okay. One last call for any questions. Hearing none. Again, thanks so much, Derek, for presenting here, and certainly I can understand doing kind of an overview here, since you've kind of just gone through some of the PDR and gotten into more of these more technical areas.
Mhm.
So, you know, with that and time for trying to work on it, won't take up any more of your time there. And certainly best of luck as it goes along, and keep us informed. We'll have to you know, keep things updated, you know, as far as sending it out to the center and whatnot as you guys progress on. So
Yeah, definitely.
all right.
That was a great job. Thank you.
Thanks.
And like I say, we've got next seminar here coming up in 2 weeks. Let's see if I can quickly pull up the calendar. Remember what the actual date of that is. It's October 6th. And I think for now that is open and free. So there's no particular person that has reserved it. So if anybody there would like to present here in 2 weeks, please email me as soon as possible. But otherwise, thanks for joining us, and have a good day.